You know, for the past 100 years, modern physics has been haunted. I mean, truly haunted by this ghost, this fundamental problem that has stopped some of the greatest minds we've ever known just dead in their tracks. But what if the answer wasn't some crazy complicated new theory? What if the solution was just fixing a tiny, simple mistake we've all been making for over 2,000 years?
And that's the big question we're tackling today. This idea that our most advanced, most sophisticated understanding of the entire universe might just be built on a cracked foundation. So let's see if we can find that crack.
So this ghost, where is it hiding? Well, it's not in some far-off galaxy. It's lurking right in the gap between our two most successful theories of reality.
On one side, you've got Einstein's general relativity. It's beautiful. It perfectly describes the big stuff, stars, galaxies, the way gravity warps space and time. Then, on the other side, you have quantum mechanics, our unbelievably precise theory for the tiny stuff, the wild, weird world of atoms and particles. Both theories are absolute masterpieces in their own right. The only problem? They can't stand each other. Seriously, you try to use them together, say, to describe what's happening inside a black hole, and the math it completely shatters. It starts screaming out one impossible answer.
Infinity, that's the ghost. Whenever your theory spits out infinity, it's not a profound answer. It's a giant flashing red light. It's the universe basically telling you, nope, that's not it. Your math is broken. Go back to the drawing board. Now, physicists are brilliant, of course, so they did figure out a way around this.
They invented this mathematical trick called renormalization. And the metaphor here is just perfect. It's like you made your soup way too salty. And instead of figuring out why, you just keep adding water to dilute it. I mean, it works, you can eat the soup, and this trick lets us make some of the most accurate predictions in all of science. But it's a patch. It's a workaround. It just sweeps the whole infinity problem under the rug instead of asking the most important question. Why was it there in the first place?
And that question, well, it leads us right to the source of the problem. A flaw that isn't buried in some super complex equation, but in something we all learned in middle school geometry class.
This right here, this idea from the ancient Greek mathematician Euclid has been the absolute bedrock of mathematics and physics for millennia. A point tells you where something is, but it has no size. It's just an idea, a perfect little piece of nothing. And that is the culprit. Think about it. If an electron is a perfect point with zero size, all of its energy gets concentrated into an infinitely small space. If a black hole collapses all its mass into a point of zero volume, its density becomes infinite. See the pattern? The zero is what's creating the infinity.
So you gotta ask, right? Why on earth did we just go with this for so long? Why did we build our entire model of the cosmos on an idea that, by its own definition, doesn't even physically exist?
Well, it really boils down to three things. One, it just makes the math way cleaner. Zero is elegant. Two, it fit really nicely with old philosophical ideas about perfect, ideal shapes and forms. And three, probably the biggest reason. On a practical level, nobody could ever prove it wrong. I mean, even if a point did have a size, it would have to be so ridiculously, impossibly small that we could never hope to measure it. Or so we thought.
And this is where the rebellion begins. A direct, head-on challenge to that ancient, sacred assumption. It proposes a whole new reality for the most basic building block of the universe. Now, this didn't come from some sudden flash of insight. The source material explains this was the culmination of a grueling 35-year quest by South Korean scientist 양동봉. He dedicated his entire career to asking the one question nobody else was asking. What if a point isn't zero? What if it's a real, physical object with actual dimensions? So, what's the answer? After all that work, this new theory gives us a number. A point isn't zero. It has a real physical size of about 1.977 times 10 to the minus 95 meters. Now, I need you to understand how impossibly small that is. It is 60 orders of magnitude. That's a 1 with 60 zeros after it, smaller than the Planck length, which we used to think was the smallest possible thing. This is it. This is the universe's absolute final pixel. You can't get any smaller. And it doesn't stop there. If it has size, it has to have mass. The theory calculates that too. It's the tiniest possible bit of existence, the fundamental seed from which all other matter in the universe grows.
And finally, it gives us the smallest possible tick of the clock, a single moment, the absolute shortest instant of time that can possibly exist. It's like we found the true frame rate of reality itself. Size, mass, time, all of it, coming from a point that is not zero.
Okay, I know what you're thinking. How on God's green earth could anyone calculate numbers like that? It seems impossible. Well, the answer lies in a completely new way of doing physics, one that combines a grand, unifying idea with the raw power of artificial intelligence.
The process itself is really incredible. It starts with this foundational idea called OPS theory, which basically says all the laws of nature, gravity, electromagnetism, everything, are just different parts of one single unified system. Then you convert all the constants of physics into pure dimensionless numbers. You strip away the meters and kilograms and create a universal language. And then you unleash a custom-built AI on this massive dataset, having it search through over 900 million combinations to find the hidden connections, a pattern that no human brain could ever hope to see.
And that's what's so amazing here. This wasn't just a human with a pencil, and it wasn't just a computer running numbers. It was a 35-year-long human quest driven by intuition, guiding the brute force calculation of an AI to find one single, coherent answer hidden in all that cosmic noise.
So, we've gone back, we've fixed this 2,000-year-old flaw, we've given the point a real physical identity. So what? What happens next? Well, the ghost vanishes, and the entire blueprint for how we see reality starts to change.
And what you get is this incredible domino effect. If a point has a minimum size, then the whole idea of a singularity, a point of infinite density, is just impossible. So the problem at the heart of black holes and the Big Bang? Gone. The cosmological constant problem, which has been called the worst prediction in the history of physics, this theory solves it. All those infinities that made us invent mathematical tricks to ignore them, they just don't even show up anymore. And suddenly that holy grail of physics, unifying general relativity and quantum mechanics, finally looks possible.
And on a bigger scale, the source points out that a discovery this fundamental could really mark a major shift. For South Korean science, what they're calling K-science, it represents a leap from just being a follower of existing science to becoming a creator of totally new scientific frameworks. It's like going from playing the game to rewriting the rule book. In the end, it's just a wild thought. By giving a real physical size to the absolute smallest thing imaginable, we might have just unlocked the biggest secrets of the cosmos. If this whole thing holds up, it means that reality itself is written in a single unified code. And now that we've finally found the alphabet, the point, the real question becomes, what else can we now learn to read?